Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide, and I'm going to be talking to you about, one moment, making sense of statistics. All right, well, let me just get going. You need statistics because things vary. You want to describe how things vary, figure out what is usual, predict the variation, and control the variation. This is particularly important in medicine. You know that people are different, and you know that they vary in terms of whatever you can measure about them and their health, and you want to create treatments that make a difference to that health. And so you want to control the way people's health varies. And that's the ultimate goal of medical research usually. So we need statistics in medical research because our goal is to control the variation. Statistics is useful for answering questions, but only questions that use data. And so when you're doing statistics, you use that data to draw graphs, or graphs if you prefer, to calculate numbers, to perform statistical tests, and to create mathematical formulas for predicting things. That's what you do when you're doing statistics. So let me focus on the questions that we're going to try and answer first. Some research questions are about a single concept. For example, how much salt is there in an avocado? That's just about one concept, the salt. What percentage of people experience joint pain? That's about one thing, the joint pain. How much cloud cover does Adelaide have in March? It's about one thing, cloud cover. Do the majority of ice creams have the amount of fat in them that the nutritional information says? That's just about the amount of fat. So that's about one idea. When we have one question about that one idea and the way it is right now. That's one kind of research question. Most research questions aren't about a single thing. They're about the relationship between concepts. For example, are science fiction books thicker than other books? That would mean that we have two concepts, the genre of the book and the thickness of the book, and we're interested in how they're related. How much of an effect does more sleep have on a student's grades? We've got grades as one thing and sleep as another, amount of sleep, and we want to know how they're related. Does chili in a meal make a difference to your body temperature? We have chili and body temperature, and we want to know how those things are related. How can you predict the air temperature from the amount of cloud cover? Again, cloud cover, air temperature, and we want to know how they're related. Most research questions in all flavors of science, especially medical science, are about relationships between things. And I draw that as this little cloud thing, where I've got a cloud for one concept, a cloud for one concept. They're just ideas at the moment, and an arrow to indicate that we're interested in how one of them is related to another. Okay. Warning. I'm going to be saying this several times because it's so important. Statistical calculations by themselves never tell you whether anything causes anything else. Statistics is just not capable of telling you about causation, about whether one thing causes another thing. That's what experimental design is for. So you need to know about experimental design because without good experimental design, you can't tell whether anything causes anything, even with statistics. Once you've got a good experimental design, the statistics can help you make that conclusion, but the statistics by itself does not do that. So this diagram of concept causing concept is not really what we're getting at with statistics. We can only really answer this sort of question with statistics, that they're somehow related to each other. They might not even cause each other. They're just related somehow. Okay. So in order for statistics to help, you have to turn concepts into variables. Statistics questions don't work on concepts. So science questions are about concepts, statistics questions are about variables. And a variable is anything you could write down about somebody or something. So for example, in the research question, does chili in a meal make a difference to your body temperature? Chili could be measured as whether a meal has chili or not, yes or no. And that counts as a measurement in the statistics sense. The classification of the meal as mild, medium, or hot. So you could have 3 categories, or the exact amount of chili you added to the meal during cooking, like milligrams of chili powder. You have to decide how you measure. That's a really important part of science, and that's not statistics, the decision of how you measure. That's to do with experimental design and about you figuring out that that measurement does in fact relate to the idea that you're interested in. So that's a science thing, not a statistics thing. So I started with pictures that were clouds. And then I can turn them into pictures like this. And I draw variables as nice rectangular boxes, which are all neat and well defined. That's why we have to turn things into variables, because statistics only works on things that are well defined. I'm going to say it again. Warning, statistical calculations by themselves never tell you whether anything causes anything else. That's what experimental design is for. But statistics can help you calculate what you expect one variable to be from other variables. So we can put our arrow back the way we thought. But this arrow isn't about whether that variable causes the other one. It's just about the fact that I might be able to use one variable to calculate what I expect the other one to be. So for example, I know that a higher amount of ice cream is sold at the same time as there are a higher number of shark attacks at the beach. And it's not that one of them causes the other, and it's not a causal relation. They're both caused by hot weather and by people being at the beach. But it doesn't change the fact that if you told me how many shark attacks happened this summer, I could probably make a good guess at what the ice cream sales would be, just because those numbers actually are related. And so the variables are related, and I can use one to calculate the other. So the arrow is now what direction that calculation and what the answer produces. The one that's doing the job of going into the formula to produce an answer, that's the explanatory variable. It's explaining, not in the usual sense, in the science sense of an explanation, but that's what we use it. It's explaining the differences in the other one. And this one's called an outcome variable because it's the outcome of the calculation. These have other names in other places, but this is what I'm calling them. Okay, so this is where we've been so far. Research questions are about concepts and the relationships between them, and I've got some pictures there, either a single concept or the relationships between concepts, and it doesn't just have to be two, there could be lots of concepts related together. Concepts become variables when you measure them, and statistics questions are about variables and the relationships between them, instead of about concepts and the relationships between them. Statistics can help you calculate one variable from the others, but not decide if one thing causes another. Okay, that's where we've been so far. Where we're going is to talk about what stats you do and what it depends on. Because what I want you to learn is how to choose what statistics to do based on the situation that you're in with your science. So what statistics you do depends on what type of question you're asking and information about the variables. And those things together help you to figure out what statistics you should be doing. So let's start off. The types of statistical question and the stats that go with them. The four main types of statistical question are here. There are others, but these are the main ones. And I've told you about the purpose, the type of question, and the type of statistics. So let's look at the middle column. In the middle, there are four types of questions. There's a question that's a vague question of what's going on. And the purpose of asking that question is to describe what's going on. Here is what I observe in the data I've got. And because the purpose is to describe, statisticians call it descriptive statistics. This is what you do when you're drawing graphs. And you draw a graph and you go, the relationship seems to look like whatever it looks like. Or when you calculate a percentage or a mean or a correlation, those names are names for the numbers that you would calculate from a set of data to be able to look at and say, well, this is some estimation of what's going on. This is what's happening. So that's descriptive statistics. And all research using statistics begins with descriptive statistics. You can't get away from it, and you must have a look at what's going on before you can really have a good clue of how you're going to proceed. The bottom one, what's the formula, is the ultimate goal of statistics and almost all research. The goal is to predict, to know based on this information, can I predict what this information is going to be? And so for a mathematician or a statistician, what we're looking for is a formula that we put all these things into the formula, it spits out an answer and go, aha, that's what I think the answer is going to be. Oh, I spit out, people's demographic stuff, their age and what treatment they've had and their blood pressure and whatever, and it'll do a calculation, it'll give you a risk of heart attack, that sort of thing. That's what we're doing. So that whole thing, that statisticians call that modeling. And the process that produces the formula itself is called regression. So modeling is the big idea of creating relationships between things, and regression is the process that produces the formula. And when the statisticians talk about a model, they mean a formula, basically. So that's the ultimate goal, is what's the formula? You begin with saying what's going on, and in the middle there's a couple of smaller questions you can ask. So you can ask a what's this number question. So you might look at things and you might say, well, what is the percentage of people that have joint pain? That's a question about a number. Every individual has joint pain or they don't, and you collect together all of the people who do and compare it to all the people there are, and you've got a percentage. That percentage is a number, and you want to estimate that number. But you know that when you have just a small collection of people and not all people, and in fact you can't, because you haven't got all possible people that could ever be, you know that whatever number you calculate from your individuals, called a sample, is not going to be the exact number for what you expect for everyone. And so you give a range of possible answers, and that range of possible answers is called a confidence interval. So the interval is a mathematical word for a range of numbers, and confidence means, well, how confident are you that the true answer is in here? So that's what confidence intervals are for. So if you have a what's this number sort of question, then what you'll be doing is confidence intervals. And the last one is to decide. The purpose is to decide the answer to a yes or no question. And that is done with the process called hypothesis testing. And hypothesis testing involves test statistics and p-values. So if you ever see a test statistic or if you see a p-value anywhere in a published article, you know that that has come from a hypothesis test, and you also know that the purpose of that p-value is to help answer a yes or no question. Most statistics that people do in papers and whatever is built upon asking those yes or no questions. They'll say there is a significant relationship between these things. And that has been asked the yes or no question, is there a relationship or not? And the p-value, the hypothesis testing, is trying to help you decide that answer. So this one, highlighting it, is really, really common. It's one of the most common things you'll see in research articles. And that's why I'm going to focus on just that for the rest of this seminar. So as an interlude, let me talk about what hypothesis tests are for. Hypothesis tests help to decide answers to yes or no questions. Hold on to that. Every p-value has a yes or no question it's trying to answer. And this is how people create hypothesis tests. There are other videos about this, say on the Maths Learning Centre website or elsewhere in the world. I'm just giving you a quick pass of the general vibe, and if you want to know more about it, you can look at other videos. But for right now, let me just talk this through. This is how you create a hypothesis test. This is how statisticians create them in the first place. You imagine a world where one of the answers, yes or no, there's only one answer it could be, it's either yes or it's no. You imagine a world where one of those answers is true. And what you have to do is you have to pick whichever answer has only one way to be. So if you ask, is there a relationship between these things? Well, there's only one way to not have a relationship. Not having a relationship means that this thing, it doesn't really matter what it is, this thing will turn out roughly the same on average, regardless of what this is. There's only one way to just not be related at all. But there are many ways to be related. And so when your question is there a relationship? The answer you pick is no, because there's only one way to do that. But if your question is the percentage of people who experience joint pain, is it 50%? Is it like a majority? Well, there's only one way to be 50%. There are many ways to not be 50%. And so the answer you're going to pick is yes, it is 50%. So it's not about yes or no, it's about having only one way to be. And the reason is because we're going to have to do some calculations. And it's much easier to do calculations if you've got one number rather than a range of possible numbers to begin with. So this answer that has one way to be is called the null hypothesis. The null refers to no, and that's because it's very common for your question to be, is there a relationship? And the answer you pick for the null hypothesis is no, there is no relationship. And that's what null means. So the next stage, once you've imagined that you're living in that world where that answer is no or yes, but let's say no, then what you do is you have to choose a calculation you can do from your data so that you can know all the answers for that calculation that could possibly be ever. no matter which data you picked, and how likely all those answers are. Now that seems like a big ask. How can you possibly know all the things that it could possibly have been? And that's where probability theory comes in. So that's where mathematicians work on probability stuff and they go, cool, this calculation you can do, I have no idea what the possibilities are and how likely they are. Or maybe I know some of the possibilities, but not really how likely they are. But this calculation, I'm certain that these are all the things it could have been, and this is how likely they all are. And that is why these hypothesis tests have specific letters that they're called T or U or whatever, because the statisticians have decided that that one is the one that they know what all the things could have been. And that number is called a test statistic because you use it to do a test. The next level is you need to think about, you need to collect think about how likely the test statistic you got from your actual data is compared to all the answers it could have been. So you get that number that you think, yes, I know what all the possibilities are. You get your specific data and you calculate your one number and you think, I'm going to compare that to all the numbers it could have been and think, how likely is that compared to everything that could have happened? And that likelihood is a p-value. It's a probability. That's what P for probability. And then you have to choose a cutoff where you declare that a p-value counts as low. So if you go, this thing, in the land where the null hypothesis is true, in the land where there is no relationship, how likely is it to get this number compared to all the other numbers it could have been? And you get a probability and you get, 3%. That seems low. You have to make a decision of what really is low. And that's called the significance level. And it's usually 5%, but it doesn't have to be. So then the final thing, that's how you create the hypothesis test, that table there. But if you want to actually do it, so you do all those calculations and you get your p-value at the end, if the p-value counts as low, then you think my data is unlikely in that null hypothesis world. And so I think the null hypothesis world is not the place where I live. Or if the p-value is high, you're going, well, that's totally possible. It could totally happen if I lived in the null hypothesis world. So I reckon it's possible that that's where we live. And so you either retain or reject the null hypothesis as the official words, but that's not really important because when you do medical research and you write about medical research, you never talk about null hypothesis. The null hypothesis is just there to help us do the mathematics that makes the hypothesis test. You don't talk about null hypotheses when you do research. You just talk about what thing you're investigating. You say, I'm interested in the relationship between these things. And I did some statistics and I have decided that there is no relationship between those things, p-value. So I don't want you to talk about, and neither do any of the other people who teach you in this course, so I don't want you to talk about null hypotheses. I just want you to know that they're there. Okay, that's the end of that interlude. So the other aspect, you've got the type of question. The other aspect is the information about the variables, and that changes the statistical calculations that you can do. So let's talk about the information about the variables. The first and most important is the two kinds of variables. There are variables that are categorical variables, which are words. So things like, do you have joint pain? Yes or no? Or the chili level, is it mild, medium, or hot? Okay, those are words and they are categories. Now, sometimes you write these down as numbers, but you can tell if they're really numbers because if they really were numbers, then when you subtract them, you could tell how far apart they are, and that distance apart would mean something. Okay, so mild and medium, you can definitely tell that medium is more hot than mild, but you don't know how much more. They're just more. So if you can't calculate how much more one is than another, then it's a categorical variable. And I draw categorical variables as boxes. Those boxes are the categories that you're going to put individual things in. The other type of variable is a numerical variable. A numerical variable is an actual number. And you can tell it's a number because how far apart things are means something. And I draw those as a scale with an arrow on which to locate your number, because numbers can be located on a scale. So these are the two kinds of variables. I'm going to give some examples in a minute of different kinds of variables, so bear with me. But I also need to warn you that these variables are called by different names in different disciplines. So if you're Googling on the internet or you read a book or you look at a paper, they may call them by different names. Okay. Next thing I need to say is that subjects in the statistics sense are sources of variables. So in the medical research sense, a subject is, the person who's in your research study, But from a statistics point of view, a subject is just a thing that produces variables. And so, for example, a banana, you could write down how old the banana is. You could write down its variety, how, what type of banana it is. You could write down the weight. You could write down the amount of potassium that you found in the banana. And that banana is a subject and it produces variables. Age is a numerical variable because you can write it down as a number. Variety is a category. You can only put that as words. Weight is a number. Potassium is a number. Now, you can also calculate the potassium per 100 grams, which is what you'd put in like a nutrition information box. And that is also a variable. Even though I calculated it from the other ones and didn't measure it directly on the banana, that doesn't matter. It still belongs to that banana. It still belongs to the subject. And it's still a numerical variable. So in my chili story, I could give all my friends a meal with chili and half of them a meal with chili and half of them a meal without and measure their body temperature. It's not necessarily a particularly well-designed study, but my friends have been very gracious and I don't want to do too much to them by letting them do this chili experiment. Chili is in this has two categories, so presumably it's chili, yes chili and no chili, and that's categorical, and temperature is a number. I could have a petri dish in a lab, and the petri dish itself is my subject. I could write down a culture medium, there might be agar and just plain water or something else. I can have a treatment, maybe some of them have penicillin and some of them don't. And I can count how many colonies there are on day 1, and how many colonies there are on day 2, and how many colonies there are on day 3. I've got 2 categorical variables, culture medium treatment, and 3 numerical variables. And there's nothing stopping me using those 3 numerical variables to calculate some sort of growth rate, which is another numerical variable. And all of those things belong to the petri dish. Even though they're measured at multiple different times, they still all belong to the same petri dish. And finally, subjects don't have to be single objects. It could be a single person, or it could be a class in a university, or it could be a whole university, or it could be a country. Subjects can be anything. So in particular, I could have a group of people and a whole group of people with chili and a whole other group of people without chili. And I could write down the mean temperature, so the average temperature for the whole group, or the percentage above 37. So the reason I put this here is that when you think about the mean temperature, it doesn't belong to any one of the people. It belongs to the whole group. And so since that number doesn't belong to one person, that means that when I'm thinking about that number, the subject is the group as a whole. And the percentage above 37 also belongs to the whole group. If one person left the group, that percentage would change. It belongs to the group, not to any individual. So it's very important to realize that percentages and means belong to the group as a whole and don't belong to the individuals. The decisions we're going to make about which statistics goes with what are to do with what we write down for each individual, not what we write down for the group. Because when we do statistics, we record every individual separately in the data. We don't just record the group statistics. Okay. So there's something that sort of came up in that last one. Categorical variables belong to the subjects in different ways. So here's an idea. I'm interested in whether chili makes a difference to temperature. I can't really decide that. I can just know that chili in a meal and temperature afterwards are related to each other. There could be anything that goes on there, but I can turn them into variables like this. Yep. So the chili could be a categorical variable with 2 categories. The temperature could be a number, and I give half the people chili and half the people not chili. So in this situation, I can try and figure out some sort of formula that tells me based on the chili what the temperature should be. And so this is what it looks like. Okay, but what if I did this experiment? What if I gave everybody a meal with chili and measured their temperature, and then at a separate time gave everybody a meal without chili and measured their temperature again? Now everybody's got 2 numerical variables measured on them. But I have a problem. I can't fit this into my cloud diagram because I have 2 numbers on the left-hand side there with the temperature, and I don't really have any chili on the right-hand side because that chili is just part of the heading, the name of that variable. It tells me when to measure that variable. And so it doesn't make any sense. I need some way of thinking about my subjects so that I can write down for each one what the chili was and what the temperature was. And the way to do that is to say, just a second, every person is going to count in my data twice. I'm going to have a chili meal combination. So my meal, that person's holding a plate there, not chili meal combination, a person meal combination. Person with a meal, they either have chili or they don't in that meal, and then I measure their temperature. I will definitely have to record somewhere in the data which two measurements belong to each person. That's necessary and never goes away. But now at least I can still talk about this as chili making a difference to temperature. It's just that it makes a difference to every person individually rather than to the people as groups. So that's great, but I can't tell from the picture which of them it is. So I want to create something in my picture that allows me to see the difference between those situations. In this one, every person belongs to both chili categories. And so I'm going to draw a person and put an arrow to say which categories they belong in. Whereas over on the left-hand side, different people are in different categories. So those are the two main ways to set up data collection, and they make a difference to how you do your statistics. So the right-hand one, this left-hand one is called independent groups. The categorical variable belongs to the subjects in such a way that it produces independent groups. One group with one outcome and another group with an outcome. One group with one category and the other group with another category. But this one is called repeated measures. What the categorical variable tells you to do is to measure everyone twice, once in one situation, once in another situation. So that's important. Think about, with each person, have they been measured, has the outcome variable been measured multiple times in different, everybody's in all the categories, or has it only been measured once per person with each person in a different people in different categories? That's important. Last thing, the distribution of numerical variables. The distribution of a variable is all the things it can possibly be and how likely they are. I've talked about that before, and you can talk about the distribution of test statistic, but I'm talking about the variables that belong to individual people. So these diagrams are diagrams of distributions. This one on the left, it's more likely in the middle. The height is how likely that number is. It's much more likely to have something in the middle because it's really high there, and it's less likely on either side, but it's roughly the same likelihood on the left as it is on the right. Whereas these ones on the other side, they're more likely so the top one is more likely on the right-hand side than it is on the left. And the bottom one's got two places where it's quite likely to be. So that's important to consider. This left-hand one is an approximately normal distribution. A true normal distribution is nice and smooth and exact, but we never know that for sure. And so I'm not going to draw one that looks like that. I'm just going to draw one that's about right. The right-hand ones are just not normal. And whether it's normal or not normal is going to make a difference to how we do our statistics. And the reason it makes a difference is we're calculating a probability, that p-value. And that p-value can only be calculated because we know all the possibilities and how likely they all are. So if your original data has different ways, that's likely in different places than other places, then it will change the way you calculate that probability. So if it's normal, you'll calculate the probability in one way. And if it's not normal, you can come up with a way of figuring out the probability anyway, even if you don't know that it's more likely in the middle. Okay, sweet. So here we have it. Information about the variables changes the statistical calculations you can do. You need to know how many variables are involved, 1 or 2 or 3 or whatever, what kind of variables they are, whether they're numerical or categorical. For the categorical variables, you need to know whether there's 2 categories or more than 2. It usually doesn't really matter how many more there are, but it's 2 or more than 2 makes a difference. For categorical explanatory variables, you need to know whether they go with independent groups or repeated measures. And with numerical outcome variables, you need to know whether the distribution is normal, but just be aware, it probably doesn't matter if the sample size is large, and you can use whichever one goes with normal when the sample size is like 50 or more. So I put all this into one picture. In this picture, I have chili as a categorical variable, being used to calculate the differences in temperature, which is a numerical variable. My numerical variable is normally distributed, and my chili variable tells me to put people in separate groups. That is all this information all in one diagram. And I put it there so that I can compare things and be able to know which statistical situations are different to which statistical situations and therefore make the decision. So here is 13 common hypothesis tests. And I know they're all very tiny there, but each page of this mentions different hypothesis tests. I'm actually going to switch from the PowerPoint to my document camera, this thing here, so that we can look at them in a slightly different way. Okay, so here's my first one. It's the unpaired t-test, which is also known as the independent samples t-test. There are also other names for this, but these are the most common. Sorry. So the independent samples t-test goes with this situation, the same situation that I described with my chili. So let's see if we can change one aspect of this and see what it does to the statistics. There is no naming system for these things. It's just, I'm sorry about that. It's called a t-test because the test statistic that we calculate comes from a t distribution. Okay, so the first thing I'm going to do is do the two situations that we talked about, and we could compare them and say, well, what would happen? This is when the categorical variable describes independent groups. This is when the categorical variable describes repeated measures. So each person has had a meal both with chili and without, and I've recorded the temperature in both for each person twice. So the difference between these is this. Everything else is the same. Both numerical variable outcomes, categorical and numerical, both normal variable things. This is still a t-test. So that situation, categorical to numerical, goes with t-tests, and a t-test is either unpaired, yes, or paired. And the pair that it's referring to is the pair of measurements that belongs to each person. Each person has two measurements of this, a pair of measurements that belong to this outcome thing. Okay, so that's that. That's t-tests. I just want to point something out. The unpaired t-test is also able to answer questions like this. What if your blood pressure at the age when you're 50 is able to allow you to predict whether someone has a heart attack or not? Do you remember what I said, that statistics is not actually able to tell causation? That's right. Okay, so if I wanted to do, if my question was a prediction question of can I use, of how do I use this to predict this, then I would definitely need to use a specific technology that does that prediction. But if all I want to know is there a relationship at all, a yes or no question, well, my computer doesn't really know what order these things are collected in. And so it could be one way or the other, and it could still answer the question. And so I can still answer the yes or no question of are these things related using the t-test, even though they were collected in the opposite order. Okay. All right, well, let's change this another way. What if, instead of changing the way the categorical variable tells you to set up the experiment, what if instead I changed one of these variables? So instead, I'm going to change this numerical variable to a categorical variable. And I haven't put people here with the independent groups here, because this is an outcome variable. And outcome variables are pretty much automatically separate groups. That gets really complicated. So change this, and now this is called the chi-square test for association. There are other ways to assess this as well. The Z test for two proportions is another one, but the chi-square test is the most common. So when you see that someone did a chi-square test, it's because this is the situation that was happening. That there was a categorical variable, that they're interested in its relationship to an outcome category. This might happen if instead of taking an actual thermometer to measure all my friends' temperature, I just asked them, do you feel hot or not? And they've said, yes, I feel hot, or no, I don't feel hot. So now temperature is a categorical variable. So this is important. Do you know how I said that the way that you choose to measure your variables makes a difference? It does, because you do different statistics. And the reason it's different is I can't calculate averages of yeses and nos, but I can calculate averages of numbers. And so the calculations I do are different. The thing I also want to say is that chi-squared tests, it doesn't actually matter how many categories you have. When there's 3 categories here or 3 categories here, or 7 or 5 or 2 here and 6 here, still chi-squared test. It's extremely flexible as the chi-squared test and can use any number of variables. T-test only goes with 2 variables here. It's probably a useful place to ask ourselves, well, what would you do if you changed the number of categories? I keep saying variables instead of categories. I'm very sorry. Oh, that's a bit clearer. Sorry about it being so fuzzy before. T-test, exactly the same situation. Both have a numerical outcome that's normally distributed. Both have a categorical explanatory variable, and they're both the categorical explanatory variable is defining independent groups. For this one, there's only 2 groups, and this one, there's 3. This situation is for ANOVA. ANOVA can have any number of categories here, and it'll still be ANOVA. It's flexible in that way. In fact, it is technically possible to do ANOVA in this situation as well. But this was invented first, and this one makes it easier for us to do some other calculations like confidence intervals if we do the t-test. So ANOVA tends to be used only for 3 or more categories. And it just answers the question of, are these things related? It won't tell you whether it matters which category you're in. You're going to have to do a t-test to do that. So you'll usually say, yes, there is a relationship between this category and this number. It does make a difference which category you're in. But then if you want to say, well, does it make a difference which of these 2 categories it's in? Now that is t-test. So that's the difference between ANOVA and unpaired t-test. When we changed that for the chi-squared test, it didn't really matter. It was still called a chi-squared test either way. Okay, that's ANOVA. So I just want to point this out. We had a paired test, an unpaired t-test and a paired t-test. We had a chi-squared test, which was the same idea as the unpaired t-test, but with a categorical outcome. What about the one here? What if we have a explanatory variable that has 2 categories that defines repeated measurements, but the measurements we have were categorical? This one. Well, that's called McNemar's test. And as I said, there's no naming strategy. It would be really cool if this was called the t-test and the paired t-test, and this was called the chi-squared test and the paired chi-squared test. It's not that. It's named after the person who invented it, McNemar. McNemar's test. Now, McNemar's test only works when there's 2 categories here. It's not like the chi-squared test that's flexible that way. It's only when there's 2 categories here and 2 categories here. There are other tests that go with more categories. Okay, so this idea of drawing the picture and comparing what you've got to the other pictures that could be is a really useful way of making the decision of what stats goes with what. If you want to know more about how these things actually work, well, you can talk to us at the Maths Learning Centre if you belong to the Uni of Adelaide, or you can look it up online, but at least you've got a beginning of the situations in which it's used. So last thing I'm going to do is wonder what would happen if I changed this one. So what if I change this one to a numerical variable? Well, in that case, then that's called regression. It's called simple regression because there's only 2 variables involved. And technically, regression answers a predict question, but along the way, while you're doing it, your computer will automatically also produce a hypothesis test along the way. And so you use regression in this situation. All right, well, what else could we change? Let's have a look at these. The unpaired t-test, the paired t-test, and ANOVA. If I'm very lucky, I can fit them all on my picture at the same time. What else could we change here? We could change what this distribution is. What about the ones that have a not normal distribution here? Well, each of these has a version that goes with that situation. Getting very fuzzy now. The unpaired t-test, if it was normal, if it wasn't normal, you do the Mann-Whitney test. If it was ANOVA, you would do, the Kruskal-Wallis test. And if it was a paired t-test, you do the Wilcoxon-Sign-Ranks test. And these are called non-parametric tests, and that's that. There are a whole lot of other ones, and I've put the pictures in the PowerPoint, and we can talk about them whenever you like. But this is enough to make the decision between the most common ones. Thank you. All right.
Sorry.
No, I knew it was a risk. So.
Well, Dave was recording a maths lecture while we're standing, and that all just went, ooh.